All right, let's talk about rotation. So the first thing we need to talk about, just like if you remember way back when in Chapter 2, Chapter 1 we just talked about measurement and units and stuff. In Chapter 2, the first thing that we needed to nail down before we could start doing more interesting physics was just how do you talk about like where things are and how fast they're going. So those basic position and motion variables, and that's the same place we need to start at here. So let's just think about here what are the variables that we have in non-rotating frames, so just like our linear motion. We'll just think about one-dimensional motion here. We have position, which we called x. This is like the linear version of things, and we'll make a rotational analog of that. So position is just x, velocity and acceleration. So for rotation, when we talk about rotational position, we are going to talk about an angle, theta. When we talk about rotational velocity, we will talk about, we usually will call this angular velocity, and we're going to call that, this is a lowercase omega. And acceleration is lowercase alpha, which kind of looks like a fish. And I guess that kind of looks like somebody's butt. So theta, omega, and alpha. It's a good idea, I think, to know what, of course I know you know this is theta. That one's been kicking around for a while. Lowercase omega and lowercase alpha. Those are our rotation variables. Now, what are some of the relationships that we know from calculus? Well, we know that the dx dt is equal to v, and likewise d theta dt is equal to omega. I know that if I want to find, oops, getting ahead of myself there. I want to find acceleration and I know velocity, I can take the derivative of velocity to get that, and likewise d omega dt gives me angular acceleration. All right. What about average type? Oh, let's continue with the calculus stuff. So if you wanted to know displacement, then you could find displacement or delta omega by doing the, this is the side where, sorry, delta x, and you know velocity, you could do that. And so likewise, if you wanted to know delta theta, and you knew your angular velocity as a function of time, you could do that. And you can find change in velocities too by doing the integral. So anyway, the point of all that is all of the calculus relationships where to go this way we take derivatives with respect to time, and to go this way we take integrals with respect to time, and or antiderivatives. And same thing here. All of the same relationships persist. All right, and let's see what else. I guess sometimes we need to find average. So if you wanted to find average velocity, well, average should just put you in mind of like an actual slope, not calculus. So that's just delta x over delta t. And likewise, if you wanted your average angular velocity, you would just do delta theta over delta t. And average acceleration, I mean, come on, everything that we want to be true. Like the analogy is just, it's complete in every detail. So, almost seems silly to write all this stuff down, doesn't it? I mean, it's just everything you want to be true is true. All right, that is pretty much all we need to say. Oh, except for the fact that if angular acceleration is constant, then we have a set of, well, what's true if regular, if you're in the linear mode here? What's true if acceleration is constant? Well, if acceleration is constant, then you can use the kinematics equations. If angular acceleration is constant, then you can use the rotational version of the kinematics equations. So let's think about what those are. There's a kinematics equation that says final velocity is equal to acceleration times time plus initial velocity. So there must be a rotational one that says final velocity is equal to acceleration times time plus initial velocity. So I'm going to say the regular linear versions of them, and I'm just going to write down the rotational analogs of those things. There's one that says that position, or the change in position, is equal to 1/2 a t squared plus vi t. And I said a and v, but I wrote down the rotational versions of those things. There's no rotational version of time. That's just time. So let's see, what else? There's another one that says, let's see, this is like the average of the velocities times time. Sorry, I was going to write delta t, but we usually just write a t there. And there's one more that's often handy. So all those kinematics equations, there they are. They show up on the equation sheet. I wonder if I have a copy of it. I might have one in this gigantic mess of papers in front of me. But anyway, when you see the next updated version of your College Board issue equation sheet, it's going to have some version of these, just like the versions that they have of the linear ones. So they'll be there, but if you know what's what, you can very easily recreate them. So that's where we are with our rotation variables, and I think that's all you need to know to get through the first problems. Let me just make sure that is true. We're just going up through, 25, and yeah. Yes. So that's all good, and you might be wondering, well, what about the rotational analog of force? That's what we did next, right? When we got to chapters 5 and 6, started talking about force. And then in chapter 7, what about energy? Is there, what's going on there with energy? And then what about momentum? So all of those things will be the subject of what we do for the rest of this chapter and on into the next couple of chapters. 10 through 12, we are going to be stuck in this rotation stuff. Just kind of flipping through the problems there, I just want to maybe add one quick little bit of information here. What about units for these things? If you want to be able to do calculus, and we do, because we love calculus, it's very handy when you're doing physics, then you need to be measuring your angles in radians. which kind of is a little bit of a departure from how we've treated angles. Angles were just, for us, often just like, what's the launch angle of something? They weren't dynamic. They weren't changing over time. As soon as we get into things that are changing over time, that's when you feel like maybe calculus will be helpful, and that's when you need to commit to using radians. So the units are, for theta, we will just measure in radians, and then for omega, that will be radians per second, and for alpha, that will be radians per second squared. And I need to point out a relationship to you also, that in a circle, like, what is a radian exactly? Well, a radian, if this is a circle of radius r, and this right here, this distance, which we call an arc of length s, and if this is angle theta. If you measure theta in radians, there's a very nice relationship here, which is that theta is equal to, if this is the unit circle and this is just 1, then theta is just equal to s. Like, this is the radian measure. If it's a circle of radius 1, then that's pi over 2. The whole thing is 2 pi, and so on. So in general, if it's a bigger circle or smaller circle, you just have to scale by that radius, and that theta is equal to s over r. That's kind of like the definition of radian measure right there. If it's the unit circle, great, then theta is just equal to the arc length. So if that's true, then note that the s, the distance, is equal to r times theta. And this gives us a way of getting back and forth between distances, right? If we're talking about speed and we want to know how much distance was covered, and our angular variable. And if these things are changing, then the derivative of this s would be velocity, right? Because that's how much distance is covered. If that's changing, then the rate that it's changing at, that's your speed. So that would mean that the v, the speed, is equal to r as a constant times the derivative of this is omega. And then also, if you take the derivative of velocity, you get its what we call its tangential acceleration. That's like the rate that its speed is changing at in the circle. So I'm going to just put a t there. That's its tangential acceleration, is equal to r times alpha, right? Not to be confused with centripetal acceleration, which you would have to find otherwise. So those are very important relationships to know, and they all come just from the definition of radian measure. I think that maybe one other thing I should put in the notes. This is a thing that does not show up on your equation sheet. I think maybe this one shows up on the equation sheet from the College Board. It's either this one or none of them. I'm pretty sure that those do not. But they're very, very easy to remember, I think. Obviously they're all just multiply your angular version by r and you get your linear version. And then another thing that doesn't show up on the sheet from the College Board, I just guess because they think it's real obvious, is if you have something moving in a circle, then the speed, notice that does not have a vector hat, and so this is just the speed that it's going at, is equal to distance over time. So speed is equal to distance, that's the circumference, 1 lap, and then when we use this capital T, we mean period, which means the amount of time it takes for 1 repetition or 1 lap. So distance of 1 lap divided by time for 1 lap. And of course, you know that if somebody's talking about revolutions per minute or something like that, what's a revolution? Just remember for conversion purposes that 1 revolution, of course, is equal to 2 pi radians. There's a magical thing that happens with radians where if you're looking at units and trying to manage the dimensional consistency of your physics work. In other words, make sure that units cancel out so that you get the right thing at the end of your problem. Radians have this magical property where they just kind of appear and then they disappear. Like, for example, if this distance, which we would measure in meters, is equal to r, that's the radius of this, which is in meters, times theta, and, well, meters would have to equal meters. Meters can't equal meters times radians, but this is measured in radians, so what gives? What gives is that a radian measure is the ratio of two linear measurements. So it's actually dimensionless. We usually write that radian in, but a radian is actually just a dimensionless ratio of distance to distance. So in that way, because of that, radians can just like pop into existence when they need to be there and then disappear when it seems like they shouldn't be there. So if you're wondering like where are the radians coming from, it's because they're kind of like ghost units. Ooh, spooky. I think that's good. I think that's all you need there, and you'll have more assistance in the video of me doing the homework problems.